right, so quick outline. We have a lot of material to go through today. Like Jeff said, if you guys have any questions, just feel free to interrupt me. There's no problems with it. Now, why Rust? The Microsoft Research Center has said that has come to the conclusion that about 70% of vulnerabilities found in critical software is due to memory safety, rooted in memory safety one way or another. Of course, this is not the only reason why we're switching to Rust. However, it's a big reason. Apparently, Google came to the same conclusion when they analyzed Android and Chrome and other projects they had internally. Now, other than the benefits of Rust from the point of view of memory safety,
Excuse me.
that actually,
Excuse me.
go ahead. Go ahead.
Yeah. Are you gonna distribute this file to us or?
Yeah, we can give you the PDF, no problem.
Yeah. Otherwise, yeah, save us some.
Yep.
Thank you.
No problem. Right. So other than the memory safety benefits, which is actually guaranteed in compile time, a bunch of them. So meaning that a whole bunch of the 70% of bugs, a big chunk of them, they're impossible to go into production unless you go into unsafe Rust. But we can leave that for later. If you stay in safe Rust, uh, a large chunk of those 70% of critical memory safety bugs, they are impossible with the language. So other than that, Rust appears to be loved by engineers. Stack Overflow has year after year they do this analysis of the most loved languages, and Rust has been picking up interest year after year. So every year we see more interest in Rust. It has a very modern type system, which is also very strict. It's much more strict than C or C++ type system. However, it does not have garbage collection, which is very good for us in low-level system software type setups. And the toolchain that Rust provides, it comes with the language, so we don't have to battle with CMakes or Makefiles or Meson or whatever it is. So the build system is part of the toolchain that comes standard with the language. Cargo is extremely powerful. It's a build tool. It's going to manage your dependencies. It can scaffold a little project for you. We're going to have a little look at that in a few minutes. Rust Analyzer is a standardized language server implementation for the Rust language, meaning that you get IntelliSense type completions and hints and inlay hints and all of those. RustFMT is the standardized formatter, and Clippy is the linter. Yeah, so there's two main ways to install Rust. If you're on a Unix type system, including WSL, you can use the curl script that's just going to download the script and run for you. If you're on Windows, you can use the installer. It has an installer for 64-bit and 32 bits, if anybody's still using that. Of course, if you don't have an editor, you can use Visual Studio Code or anything else you like. Visual Studio Code can be installed either through Winget, or you can download the installer and go through the process of installation manually. Other than that, there are two main extensions for Visual Studio Code that are paramount to develop Rust. One is the integration with the Rust Analyzer, and the other is even better, TOML, which is going to format these TOML files. And TOML is like a configuration language of sorts, and it's used to list dependencies and versions of those dependencies and things like that. Now, simple Hello World application you can create with just one command, cargo new. Hello World is going to scaffold a little project that all it does is print Hello World. So you get to run some Rust without writing any code. Yeah, not very impressive, but still, you start to get the hang of how to use the toolchain, how to use cargo. You do a cargo run, cargo new to create a project, and cargo run to compile and run it. So this is behind the scenes. It's downloading any dependencies you may have, compiling the code, figuring out what the binary is, and executing it. So you have a cargo run which defaults to development with the development profile with debug symbols and so on. or you can add a -- release and you'll get a release version of that binary. As for primitive data types, we have either scalar types or compound types. Those are part of the standard library of Rust. You have all sorts of integers signed and unsigned, all the way up to 128-bit wide. This architecture specific size, it's a bit weird depending on the architecture, but it's like C int. Depending on the architecture, it has one size or another. And examples of how to use them. These underscores, they can be used anywhere. It aids with readability, but you don't have to use them, but you can split the number any way you like. Yeah. Now, when it comes to overflows, there are two different behaviors. In debug builds, the compiler is going to add a panic for you. So if it notices an integer overflowing, it forces a panic, meaning that it crashes the program. And this is to force the engineer to analyze the code and decide on which option is the best. In release build, it still silently wraps around, just like C. And by options, I mean that you can decide if you're doing a carry, add, or multiply, or multiply or division and so on, or an overflowing or checked or saturated. All of these options are part of the standard library, and they are implemented for every single integer type. Floating points, you have two flavors, just like in C. You have a 32-bit flavor and a 64-bit flavor. Rust defaults to 64-bit, so if you want a 32-bit float, you have to annotate the type. Oh yeah, I forgot to say that Rust does type inference as much as possible. So here, if you don't annotate types, it's going to try to infer what the type is. If you can't infer, then it gives you a compile error and you have to annotate the type using this colon syntax. Now, Booleans in Rust, they're different from C, because in C, anything that's not 0 can be used as a true value. In Rust, only the actual Boolean true value can be true and only false can be false, meaning that the shortcut type conditionals that we can do in C, if some variable X, then do foo. That doesn't work in Rust. You have to actually add a comparison, unless, of course, A is a Boolean variable, then of course you can use it. Characters in Rust, they are always UTF-8 scalar value, meaning that they can be from any size from 1 to 4 bytes, depending on the character that you're encoding. You can directly encode the entire UTF-8. Any potential valid UTF-8 scalar value can be held in a single character variable in Rust. Tuple is just a generic way of grouping things together. It's kind of like having a struct, but the fields are not named. So to access the elements, this little guy would be a .0. So if you have a tup.0, you would get 42. Tup.1, you get 3. Tup.2, you get 254. So each type can have each element can have a different type. They can also be the same type, but then you may as well use an array. Arrays, every element is of the same type, and it's also a static size, statically allocated, meaning that they cannot grow. If you want something that can grow, then you need an allocator, and you can use a VAC, which we're going to look at as a collection later on. So strings in Rust, they are essentially an owned collection of characters. By owned, we mean that the type itself holds the buffer that contains the character. The type manages, so the string manages the buffer that contains the characters. It owns it. Values can be borrowed in Rust. We're going to talk about that later. Strings are also dynamically sized, meaning that you can push more characters into it. You can merge them. You can modify the characters, you can delete characters, you can do a whole bunch of things with them. But of course, because it's dynamically sized, then you need a working allocator, which for embedded, if we're talking about embedded, it may not exist, right? Now this stir type, it's peculiar to Rust, but it's essentially sort of a borrowed version of a string, not really, because it doesn't really grow either. It's referred to as a string slice. We're going to look at slices a little further. But for now, imagine that if I were to take this string here and I can index it with a range and I tell it to give me the characters from character 1 to 3, then I get a stir back. I get a sort of a view, a window within the string, a sub buffer of that underlying buffer. It's also immutable in this case, by the way. So functions in Rust, they look similar to the modern C++, where you put the return type at the end, but you don't have that auto keyword in the beginning. And you always define it with this fn. It describes a function, so it's always fun, then the name of the function, and arguments in parentheses, and then this arrow and the return type, and so on. So in Rust, everything is an expression, unlike C, where C has a lot of statements. Rust doesn't have many statements. Almost everything is an expression, meaning that a function produces the last value that it evaluates. Right. So that's why I don't need a return keyword here. So if 42 is the last value, then that's what will be returned from the function. Right. For things that can fail, we have this result type, which the first member here is a success type, if you will, and the second member is an error type. So it's very nice or when interfacing with the hardware, maybe the hardware gives you a failure, then instead of crashing or returning a negative error number like we do in C, you have an actual encoded error type that the compiler enforces that you actually check it. So somebody using this get temperature function, calling this function, that person has to check the result. It has to verify if it wasn't okay with the temperature or if it was an error. Okay, I thought somebody had their hand up. No. Anyway, methods, they can be added as part of a struct or any num, which is peculiar. C nums are just like integers, right? Behind the scenes, they get compiled down to some integer. In Rust, they can have methods. They take a self argument, and self is itself, right? In this case, self refers to the instance of the foo struct. And we need this impl block to define them. And we're going to look at the impl block a little later as well. Now, structs, they are very similar in syntax to C. There are a few differences, but Rust has three main types of structs. You can have a regular struct with a bunch of named fields, or you can have this unit-like struct, and this consumes no size. This is only for the software engineer, only for the source code itself. During compilation, it gets removed. And then you have this tuple struct, which it's just like a tuple, but then the type has a name. So enums are much more advanced in Rust than they are in C. They can have type parameters. You can have an enum that the unit-like enum variant is like C, but then you can have tuple-like and you can have struct-like. So an enum that contains a struct or an enum that contains a tuple. So all of these things are valid in Rust. Now, impl blocks, it's how we add methods to structs or enums. If you remember, we just defined this color struct, and I can create a constructor for it that takes red, green, and blue and produces the color as a red, green, blue cell wrapped in a self. And the impl block is also used to define traits, and traits we're going to look a little later. Oh, here. So a trait defines an interface or some sort of standardized behavior. So for example, I'm implementing here the add trait, which is actually part of the standard library. This is how, so every type that can be added together implements this add trait. If I want to add two colors, I can implement add for color, and I can describe how to do addition of two colors. And I use saturating add because just because I'm adding more colors, I don't want to wrap around to black, right? If I add so much color that I reach the maximum, I want to stay at the maximum, which is full white. We can define our custom traits as well, and we can implement those the same way. Now, pattern matching is very useful for enums, not only for enums, but they are very useful when paired with enums. So say that we have an enum with 3 different variants, and they could encode anything, let's say a command to some particular controller. Depending on the command, then we can execute something different. So the interesting thing here is that we can also do destructuring. So for example, in this brightness variant, I get a brightness as a U8, and I can destruct the B and use it for my function, whatever function I call to control the brightness, right? Rust has a few standard collections. VAC is like a dynamic array. So VAC DAC is kind of the same, but it's a DAC, right? So meaning that you can push or pop from both sides. You have a linked list, and you have 2 map implementations, 2 set implementations, and a binary heap. You use it the way that you would imagine. For a VAC, you just push to it and pop from it. For a VAC DAC, you can push front or push back and pop front and pop back and so on. And the linked list uses a very similar API as a VAC DAC. Now, a hash map is like C++'s unordered map, and the B-tree map is like a C++ map. Otherwise, they behave exactly the same. The only difference between them is the underlying data structure, which is going to give you different complexity, right? Time complexity and storage complexity. Now, SAT is the same. It's just a SAT version of the maps, very similar to C++ in that sense. Now, the difference here is that if I try to insert the same element twice, then the second time I get a false, meaning that the element was not inserted. Now, binary heap is by default a max heap. We can force a different ordering, a main heap with this reverse type, or we can create our own type that wraps whatever other type and implements its own ORD trait, an ORD for ordering, right? We can come up with our own ordering and use the binary heap in ways that were not envisioned initially. Any questions so far? Because we're going into ownership and borrows, and it's going to be a little more complex. All right. So now, ownership, it's just a set of rules that tells the compiler how to use the memory, right? How it should think about memory. Because Rust is built on top of LLVM, then it turns out that the memory model is the same as C++ memory model because of LLVM. But anyway, so the rules that the compiler follows tells the compiler about the validity of a type and the underlying memory for that type. So whenever a variable goes out of scope, the memory is automatically reclaimed by this drop, which is also a trait. We can we can, every type has a default drop implementation, but we can override it with our own custom implementation if we need to do other things. Like, for example, if I'm, I don't know, if I'm dropping a reference, if I'm dropping a driver instance for, let's say, an I2C controller driver, I can use the drop trait to cut its clocks, right? Other than releasing the memory, then I can also cut the clocks that it uses. Yeah. So yeah, anyway, I guess that's it for ownership. Now, when you get to borrowing, it starts to get a little harder because if I'm borrowing a type, then it means that I only have a reference to it. Now, Rust wants to make sure that we don't have dangling references and that references remain valid for as long as they're held, right? And 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 this is one of the reasons how it can avoid those 70% of bugs. Um, it makes sure that whenever you borrow a type, then it makes sure in compile time that the actual type, the owned version, not the reference, but the owned version, remains valid for at least as long as the reference is valid. So when I call bar with a reference to A, then I'm creating another scope, right? Now, if I were to call bar and concurrently drop A, if A goes out of scope concurrently, then the code wouldn't compile, right? Just like here, I call foo A. So foo takes ownership of A, meaning that A is not valid in this scope here. It's now only valid within foo. If I try to increment A again, then A doesn't exist anymore, right? It went out of scope from my perspective. So then we get a build error. Right. So slices, it's like I was saying before, it's just a window into elements of a collection, a contiguous window within elements in a collection. So if you have a string, you can get a slice of that string to look at a subset of the characters. You can do the same for any other collection, a vector, a vecdec, or any of those. Now, type parameters. So if I have using this example, if I have a point, I can have a point in various coordinate systems, right? I'm using polar and Cartesian as an example here, but it could be any other. Now, point itself doesn't care which coordinate system it is, as long as it's a coordinate system. So we can parameterize point and say and tell it that point just needs a coordinate in some type T, right? Now, right now, T could be anything. It could even be a U32, which is not a valid coordinate system, but we're going to look at that a little later. But anyway, so I can create a point P1 on the polar coordinate system, and I can create a point P2 on Cartesian. And Rust figures out all the types of P1 and P2 for me. I don't have to annotate them. Now, if I want to limit the value type parameters, then I can define a trait. So I can define a trait coordinate system, and I can implement it for polar and for Cartesian, and now only coordinate systems can be used on point. If I pass anything that doesn't implement coordinate system, it's a compile error. So lifetimes are another type of generic. It tells the compiler that essentially we're annotating the lifetime of these references. So say that I have a whole bunch, I have a deep function call, right? And the compiler needs to know that these references are valid all throughout. So we can annotate the lifetime with what something like that. So this quote A is a lifetime, a generic lifetime. And I'm saying that all of these references and the return type, they all must be valid for the same amount of time. So if A goes out of scope before, So if the compiler cannot prove that these lifetimes are the same, then the code will not compile. Now, Rust gives us standardized unit testing built into the language. There are a whole bunch of libraries which are called crates in Rust. So a whole bunch of crates that augment this functionality, but the basics remain the same. You have this little attributes that we add. So this is a compilation flag, actually, that this part of the code will only compile and go into the binary if I'm compiling for test. And this test attribute is how Rust figures out what's the test that needs to be run, right? And it has a few assertions by default, and there are other crates that augment those assertions as well. So whenever you see this exclamation point, that means it's a macro. So the compiler generates some extra code for this to work. So async await. So the language provides the async and await keywords, but does not provide an async await runtime. All right. So runtime is not part of the language. Runtime is an extra crate that you need to pull in. Now, all of these runtimes, they are built on top of Future, and Future is a trait, part of the Rust standard library, and it's the backbone of the entire async await technology, right? And they basically represent values that are not immediately available when you execute them. Essentially, the trait just defines an output type, a return type, if you will, and a poll method. As long as you can implement a poll method and produce a type in the future, then you can implement Future. An executor is a runtime, again, not part of the language, comes from a separate third-party crate. And it understands how to use async await functions. So these functions that produce a future, it understands how to poll those futures and how to resolve them into values that can be returned. Async functions, it's just a regular function definition, but you add async in front of it, and then the compiler knows that the return type needs to be wrapped into a future. And whenever you call await, it's essentially pausing execution, going to do something else until the future resolves. Now, whenever we have embedded code, we don't have a standard library available. So we need to annotate the code with this no std and no main. No std for no standard library, right? Then we need to implement a panic handler, and there are three different crates for it. There's panic halt, panic probe, and another one that I don't remember. And then you need, if we're talking about Cortex-M or RISC-V or AArch64 and a few others, they have these traits defined already that allow you to use bare metal, to produce bare metal for those architectures. So Cortex-M and Cortex-M RT is two of them, right? So Cortex-M RT gives you this entry, and this entry here is an attribute which behind the scenes is a macro that's just going to generate code for us that the linker can execute, right? The linker can place in take the address and place it in the vector table. Now I mentioned that async needs a runtime. So Embassy is an async runtime for embedded devices. It currently supports Cortex-M, RISC-V, and ESP32. There's a ton of HALs, or hardware abstraction layers, that are being developed. And it provides many useful building blocks for producing async code for embedded devices. So you can create tasks, you can, there's a generic timer driver, there's a whole bunch of useful utilities for us to rely on. But you don't have to use all of it, you use what you need and just ignore the rest. And basically, that's it for the overview of Rust. I'll share the presentation in the chat now.